carry on our discussion on finding the joint PDF of the function of random variables actually, and we did it for 2 random variables, and now let's do this if we have more than 2 random variables actually. In other words, if you have say n random variables x1, x2 up to xn, and you have some functions, say y1 is a random variable that is g1 of x1, x2 up to xn, and y2 is g2 of function g2 of x1, x2, xn up to say yn is gn of say x1, x2 up to xn. The question is that if we say that for these n random variables you have a joint PDF x1, x2, xn, what will be the joint PDF for y1, y2, yn? In other words, that what would be the joint probability distribution for functions of the n random variables actually. Again, you're going to have two assumptions, basic assumptions on G1, G2, Gn. The first assumption is really same as what you have in 2 dimension, that as y1 is expressed as some function of x1, x2, xn, and similarly all other y's, each one of this x1, x2, xn we should be able to express in the terms of the y1, y2, yn. In other words, we should have a function h1, h2, hn, like x1 is a function h1 of y1, y2, yn, so on and so forth, and xn is equal to say hn up to y1, y2, yn. Okay, so g's are the kind of the functions, as y's are expressed in the terms of x. G should be such kind of a function so that we should be able to express the x in the terms of the y actually. Okay, so we have this, and the second, obviously assumption is that the Jacobian of say x1 up to Jacobian of say x1, x2 up to xn, which is going to be a function, a determinant actually, okay, a determinant in which you have say partial g1 by partial x1 up to partial g1 by partial xn, so on and so forth, partial gn by partial x1 up to partial gn by partial xn actually, okay, so partial gn by partial xn. So in other words, this determinant should make sense, and this determinant should not be equal to 0. What do you mean by this determinant should make sense? Like g1, g2 and all of these gn's should be differentiable with respect to each one of these random variable actually. So all these partial derivatives must exist, and the determinant of these partial derivatives in this manner should not be what you call 0. Once your g's satisfies these 2 conditions, we should be able to find the joint CDF of the functions of the random variable in the terms of the PDF of function of a PDF of x1, x2, xn. And what would be the recipe? The recipe would be precisely same as what you have, for example, previously. In other words, that the joint PDF of y1, y2, yn as y1, y2 up to yn should be equal to what? The PDF of x1, x2 up to xn evaluated at h1 of y1, y2, yn up to hn of y1, y2 and yn actually, okay? So in other words, take your PDF, okay, and evaluate it at h1, h2, hn. In other words, evaluate it at small x1, small x2, small xn, okay? Where, I mean, if I wish, you can even write it as, for the sake of simplicity, x1, x2 up to xn, where xi is hi of y1, y2, yn for I equal to 1, 2 and up to n. So this PDF multiplied by, like in the two dimension, Jacobian of say x1 up to xn, it's absolute and reciprocal. Okay? Let me write it once again clearly. Jacobian of x1 up to xn, it's as absolute and it's reciprocal. Okay? So in order to what do you call, find the PDF of say n random variables, functions of random variables, you need to evaluate the PDF at these functions and multiply it by the Jacobian, the determinant of the Jacobian, absolute of the Jacobian inverse actually. So this is really the straight generalization of what you are doing, for example, in two dimension. Let me do one simple example based on it, and then I am leaving one example for you to make sense of it. So imagine I have three random variables. So this is an example. This is example 70 from the book. Imagine I have three random variables, x1, x2, xn, with the PDF say fx1, fx2 and fx3, no, fx3. Okay, on the three random variables and with this PDF actually. Now let me define three new random variables which are the function of these x1, x2, xn, and these are, let's say, linear expression x1 plus x2 plus say x3. This is y1. Y2 is what do you call x1 minus x2, and y3 is x1 minus x3. Okay, so these are the three things. So in other words, my g1 of x1, x2, x3 is x1 plus x2 plus x3, and my g2 of x1, x2, x3 is x1 minus x2, and my g3 of x1, x2, x3 is really, what do you call, is called x1 minus x3. Okay, so x1 minus. So these are my functions g1, g2, g3. So we identify. We need to identify everything. Now the question is, using these g's, can I find h1? The answer is yes, actually. I mean, if you treat these three equations as a system of equation, okay, in which x1, x2, and x3 are unknown, and say y1, y2, y3 are known, then we can solve this system in which the x1, x2, x3 has values in the terms of the y's actually. So I'm not going to solve that, I'm just going to directly write it, that if you will, for example, solve this system for x1, x2, x3 in the terms of y1, y2, y3, you're going to get this actually, that your x1 is going to be y1 plus y2 plus y3 upon 3, and your x2 is going to be y1 minus 2y2 plus, what do you call, y3 upon 3, and the x3 is going to be y1 plus y2 plus minus 2y3 upon 3. So we have kind of h1. So this is like my h1. This is my h2, and this is like my h3 function actually. So in other words, that each one of g1, g2, g2 is g3 is kind of, this system is kind of invertible actually. Now once you have this, what would be the next thing that you need? So we have now our x1, x2, x3. I can substitute them here. So the next thing that I need to do is to calculate the Jacobian actually. And the Jacobian of x1, x2, x3 is going to be the derivative of the g1 first with respect to x1, then with respect to x2, then with respect to x3. So it's going to be 1, 1, 1. Okay? And this is going to be 1 minus 1, 0, because there is no x3 here. So this is going to be 1, 0 and negative 1. And if you compute this determinant, it turns out that this is equal to 3. So this is your Jacobian actually. Hence, we can write now our function kind of more explicitly. Okay. We can write it, our function kind of more explicitly. And now our fy1, y2, y3 of say y1, y2, y3 is going to be fx1, x2, x3 of x1, which is this y1 plus y2 plus y3 upon 3, okay, and maybe I can just write, for example, x1, x2, x3 times the absolute of the Jacobian. So 3 is positive, so absolute of 3 is going to be 3, and it's reciprocal. So this is going to be 1 over 3, where these x1, x2, x3 are basically these values. Okay? So you get the generic formula. So here x1, x2, x3 can be, anything. Now let's assume, okay, let's apply this formula and try to compute. For example, let's take these x1, x2, x3 as some concrete random variables and try to compute an explicit formula for what do you call the y1, y2, y3. So let's assume that these x1, x2, x3 are all three standard normal, okay, distributed random variable, and they are independent actually. Okay, they are independent. Now, if this would be the case, then the fy1, y2, y3 of say y1, y2, y3 would be equal to 1/3 of the, since all three are independent, so it's going to be 1/3 of the product of each one of the, what do you call, marginal distribution, or the PDF of each one of them actually. To fx3 of x3. This is what it is going to be. Now what is, where obviously these x1, x2, x3 are any real numbers actually. Okay. So the 1/3 of, so this is example, okay, particular instance. Now what is the joint PDF, what is the PDF of a normally distributed random variable? So it's going to be obviously 1 over square root of 2 pi times e to the minus x1 square upon 2, okay, times 1 over square root of 2 pi e to the minus x2 square upon 2 times 1 over square root of 2 pi and e to the minus x3 square upon 2 pi. So this is what that you're going to get, and hence finally you will have 1 over 3, so 2 pi will become what do you call 6 pi, so it's going to be 6 square root of 2 pi, okay, 6 pi and the square root of pi, square root of 2 pi, okay, this is what it is going to be, and e1 raised to, you can sum I equal to 1 to 3, you can add the powers and you're going to get xi squared upon what you call 2, where the xi is x1 is y1 plus y2 plus y3 upon 3, and similarly you have expression for x2, and similarly you have expression for x3. So take these values, substitute them here, so you get what you call a joint PDF of 3 independent, normally distributed independent random variables, okay, are the functions of the random variables. That, okay, these 3 are joint and standard normal, and you have these functions of what you call random variables, which are standard normal, then what would be their joint PDF? So this is going to be their joint PDF actually. So I hope it got give you some sense actually that in, you can even generalize this transformation formula into the higher dimensions and compute the probabilities. I leave as an exercise, reading exercise, for you to, completely work out the example 7e. Okay, so example 7e is something for you to work out. Okay, so I hope we learned some new set of facts during these set of discussions. So, and we end the chapter number 6 at this instant. So next we will like to move towards the new chapter, the chapter number 4, chapter number 7, that is all about the properties of the expectations actually. Okay, expectation of single random variable, expectation of sum of random variables, functions of random variables. So it's all about expectations actually. Conditional expectations will compute a lot of kind of expectations, and we'll see the different kind of properties of expectations in this chapter actually. Okay. So let's start with recalling that recalling the fact actually that if so this chapter is the chapter number 7 from Ross. So properties of expectations actually. So let's recall that if I have, for example, a discrete random variable that takes, say, value x1, x2, xn, then the expectation of x is equal to the sum of the weighted probability, weighted average. So its expectation is weighted average actually, that goes from y1 to infinity, x times the probability that x equals xi. So this is what really is the expectation. And if x is a continuous random variable, okay, so if x is a continuous random variable, then the expectation of x is minus infinity to infinity, really the continuous time version of it, x times f of x and dx, where fx of x is a PDF of the normal random variable actually. And now what we're gonna do, we're gonna study, what do you call the several properties for the expectations actually. Okay, for example, imagine that if you say, okay, if you say, for example, that there is a probability that x is going to always stay between a to b, and this is equal to what you call 1, then what we can say about the expectation? So if this is true, then can you guess that what will happen? Okay. Then the expectation of x is going to stay between what do you call a to b actually. So if x is between a to b almost surely, in other words it's true with probability 1, then expectation of x should also be between 1 and 2. Probably you can treat this as a little exercise for you actually, that okay, if this is given to you, how you can reduce this result. Let me move towards what do you call the more interesting cases. The more interesting case is to basically start with, for example, a proposition. Even in one dimension we have seen many properties of it, so that the 2 and the higher dimensions is going to be kind of the more interesting result actually. Okay, I'm not going to prove this proposition because the proof of this proposition is very much analogous to what you did in the one dimension actually. Okay, so you may read its proof directly from the book actually, so I'm not going to get into that. I'm not going to get into that. But I mean, maybe I can give you some hints. So if you have two random variables, x and y, with say joint PDF, say fxy of say xy, okay, then if the discrete case, if both of these random variables are discrete, then the expectation of some function of x and y, okay, maybe you may assume that x takes the values x1, x2, x3, x2 and so on and so forth, and y takes the values say y1, y2, y3, so on and so forth actually. Okay, so these are the values, and g is a function actually. Okay, so g is some function. Okay, obviously you need this function to be at least integrable. Okay, you need at least it to be continuous actually, not necessarily continuous, but it should be a kind of a function which is integrable, for which the integral makes sense, for which the infinite sums make sense actually, especially when you are in the discrete case. Then the expectation of the g of xy is going to be what actually? In one dimension we know that the expectation of g of x is, okay, what was the expectation of g of x? So it was that, okay, you compute the g at each xi and multiply it with the probability of xi. Okay, so this is what you had actually, that okay, evaluate the g at each of the point that x takes and multiply it with the corresponding probability. So you can have the precisely same case here actually, that okay, here you have a double sum. So I have, say for example, I that goes from 1 to infinity and j that goes from 1 to infinity, and evaluate the g at xi and yj, okay, all possible ordered pairs of it, and multiply them with the probability that x is xi and y is yj. Okay, or you may write it, for example, even more precisely. So I mean, this is enough actually, that okay, the expectation of g of xy is going to be the g evaluated at each of the xi and yj multiplied by their corresponding probability. So in other words, here x was taking values xi's and multiplied with their probability. Now you are saying that okay, evaluate the g at each of the ordered pair. Okay, each of the ordered pair that you can make out of these values and multiply them with the corresponding probability of the ordered pair actually. Okay, so this is the discrete case. How about the continuous case? As per expectation, the continuous case is going to be expectation of say g of xy. In other words, when x and y are continuous random variables, then the expectation of g of xy is going to be a double integral that goes from minus infinity to infinity, minus infinity to infinity. Take the g of xy, multiply it with the joint PDF of xy, and then integrate it with respect to dx and with respect to dy actually. Okay, with respect to dx and with respect to dy. So simply, okay, multiply, evaluate the function at xi, multiply with the PDF and integrate actually. Okay, multiply with the, and integrate. Shall I do it? Let's do, for example, let me just quickly, for example, do the proof of the continuous case actually. Maybe discrete, you can do it for yourself. Okay, it's not that difficult. It's not that difficult. So here's a proof. I mean, if you remember a lemma that says that, recall a lemma that if you have a random variable, for example y, and you want to compute its expectation, you can write or calculate this expectation by integrating it, say, from 0 to infinity, not 0 to infinity, 0 to infinity if the g of xy is a non-negative function. In other words, here let's assume that your y is greater than or equal to 0, and then the expectation of y would be equal to an integral from 0 to say infinity by integrating the probability that y is going to be bigger than t and integrating it with respect to dt actually. Okay, so we proved this lemma previously. Okay, so this is not something that I'm just recalling it. Now, if you assume that okay, your y is okay, instead of y, you may write any random variable. Okay, instead of y, say for example, let's take it at z, doesn't matter, you're gonna have the same. Now let's call g of xy to be z actually. Okay, let's call z to be the g of xy. Okay. Obviously, we will first prove our this result for the g when the g is non-negative actually. But you know, as we also did when we were driving, for example, this result actually that the expectation of g of x is equal to g of x times fx of x dx. Okay, when we were proving this actually, we also proved it first for non-negative functions, and then we said that okay, now if your function is not negative, then you can write it as the sum of a positive part of the g minus the negative part of the g actually. Okay, so you can apply the same trick actually while these two functions are non-negative. Okay, I'm not going into the details of this actually. So in other words, if your result is true for a non-negative function, then for generic functions using this identity you can also deduce the same result. Okay, so therefore it is enough to show the result for the z when g is non-negative. Okay, so the expectation with this result, expectation of g of xy is going to be an integral from 0 to infinity of the probability that g of xy is bigger than t and dt. Okay, this is what